Hello everyone and welcome to PC Retro Tech. This is what it looks like on my workbench sometimes, with machines everywhere. I've been programming again, and in this week's video I'm going to be revisiting rotation of 3D objects on my XT machine, which is this one here. Has an 8088 processor which runs at either 4.77 or 10 megahertz. Everything I'll show today will actually be at 10 megahertz. So the first thing I'll do is show you where I'm up to with the original tetrahedron that we were rotating. But don't worry, we've got lots of other shapes to show off today, including at the very end an icosahedron. And then after that I'm going to go back and look at the history of rotating 3D shapes on early machines and see if we can find some early demos and games that actually rotate 3D objects. Here is the tetrahedron code running, and we had it at 40 frames per second in the previous video, and believe it or not now it's closer to 60 frames per second, and it still looks like the tips are pulling away a little bit, and that's just because of the way the animation is done and your eye notices the movement of the triangles as they're flying around. A little bit later you'll see the more complex shapes don't have this problem. Now, how did I make this faster? Well, the first thing that I did was to write a much faster blanking routine. So instead of worrying about being pixel perfect, the blanking routine just clears to the nearest byte instead of the nearest pixel. And then only the triangle drawing routine actually bothers about cleaning up the edges. And so this actually saves quite a few frames per second. And the other thing that I do is I just minimize the amount of blanking that's done. So I don't clear all the way over to here, but really only over to where the edge of the previous object was. And so that's the first thing that I did to speed this up. I'll describe a second thing in a moment, but first I want to show you what else I've done with the code. Basically what I've done is generalize the code, and now you actually enter in the data for the object you want to display in a very simple format. Basically you just write down the coordinates, just floating point numbers of all of the vertices of the object you want to display. So there's X, Y and Z coordinates for each of 4 coordinates, and then you just write down what the faces are in terms of those coordinates. So the first face has coordinates 0, 1 and 3, so that would be this vertex and the final vertex. The next one 0, 3 and 2 and so on. You just tell it how many faces and how many vertices there are, and actually this is really just a comment. So now I can actually have other objects, and if I go up to the top here I actually have an icosahedron which has, you can see, really a lot of vertices and faces, 20 faces and 12 vertices. So this means that we can display all sorts of different objects. So I'm going to go through and show you 3 others that I have. The next shape I want to show is a square pyramid. It has a square base and 4 triangular sides. It looks a little bit like the tetrahedron, but this has 5 vertices, 1 at the top, 4 at the base, and 6 faces. So 4 triangular sides, and the square base has to be made of 2 triangles. Unfortunately you don't see the base because of the way I've done the rotation here. But I want to describe the second technique that I came up with to speed everything up here. And that was to treat the machine more like an 8-bit machine instead of a 16-bit machine. After all, it only has an 8-bit data bus, and so 16-bit accesses to memory require 2 bus accesses. So instead of treating this as the edge of the screen, I decided to treat this as the edge of the screen, and then all the x coordinates are less than 128, which certainly fits into 8 bits, and that sped everything up. Now it might seem like a bit of a rookie mistake to be using 16-bit values in the first place, but it really wasn't an obvious optimization when I originally wrote the code, and certainly it wasn't easy to write the code this way, but it did speed it up and everything looks much faster now. Now of course we've got to have a cube, and that's what the next one is, but I just want to point out the pre-computation here where I'm pre-computing the rotated coordinates. And I've got that down, I think, from 20 seconds to less than 3 seconds for the tetrahedron. Of course, the cube takes a little longer because it has 8 vertices and 6 faces. Now, this still looks a little bit rough, and I'll talk a little bit about why that is in a moment. But one of the things that I did to make it less rough is to put all of the code that does computation before the code that does image drawing every frame. And so that means that the image stays on the screen for longer while all the computation is being done, and that makes things look a little bit more consistent to the eye. So I have to say that this whole thing was not a beginner project. I think there's something like 1,000 lines of C code and maybe a couple of thousand lines of assembler. And some of the assembler I rewrote like a dozen times. I'd make a mistake, I'd just have an idea that was just totally wrong, or I'd run out of registers, or it just wasn't faster, it would actually go slower, and so on. So I've actually really worked like crazy for about the last month, in fact, to get the code into this new state where I can do multiple different objects. But it's still a very fulfilling thing to do, and I encourage you to try out assembly if you haven't before in graphics programming, even on these old machines. It is a lot of fun, and yeah, you can really get some really cool stuff going. Well, here it is, folks, the icosahedron rotating at, believe it or not, 30 frames per second. So the icosahedron is a shape with 20 faces and 12 vertices. So there's one vertex at each end and 5 vertices around each end. I think this looks very smooth, and this is really down to the fact that the triangles are very small, and any blanking that's done around the edges of the object is done immediately after the adjacent triangle is drawn. So there's almost no gap in time between those two events. So you never see any jagged edges before they get cleaned up. It's also nice that we have the alternating colors instead of just flat colors, so that we have a little bit of a pattern, and it makes it look like there are a lot more colors than just the 3 plus black. This could be sped up a little bit. At the moment, the only things in assembly language are the triangle drawing, the line drawing, and the blanking routines, and that could be improved by making the C code that does all the rest of the rotation and updating everything in assembly language as well. So I don't know how much faster that would go, but at some point I'll work on that, of course. But this is basically as far as I'm going to go with rotating 3D shapes on the channel. What I'm going to do for the rest of this video here is answer a viewer question. So he asked, well, is it really that hard to do 3D rotation on these machines? After all, there were CGA games that had 3D rotation. And my immediate response was, oh, no, that's pseudo 3D, it's not real. But he actually gave a list of 3 games which, lo and behold, when I run them on this machine, they do work, and they do actually have true 3D. So we're going to take a look at those, and also some demos, very early demos that actually do some 3D rotation. Now, I can't go without talking about the 8088 MPH demo by Hornet, CRTC and Desire. This is an 8088 demo, but it runs on the original IBM PC, so at 4.77 MHz, which is half of what I'm running my XT at. Now, it's still CGA, but there are more colours here because they're using composite mode, and also because they developed their own tricks to get a lot more colours using NTSC artifacting. So I think there is some pre-computation, because before this starts there's some text that scrolls up and down the screen for a while, and that's a very likely place to hide pre-computation in a demo. But when this tetrahedron starts rotating, it doesn't take long before it repeats, and that's a hint that they're actually doing a lot more pre-computation. I don't know for sure, but it's possible that they're actually pre-computing almost everything except the actual drawing itself. And what they do, according to Scarly, who wrote this part of the demo and also a blog about it, is that they use a span buffer which records the start and end points across each line where the colours change, and then they intersect these span buffers so that they can record the difference between 2 frames. And I suspect that may be what they're actually pre-computing, although I really don't know that for a fact. Now, the other thing that happens in this demo is they do dithering on the faces of the objects. Now, it doesn't seem to be here on the tetrahedron, but you'll see when the cube comes up that there is a kind of pattern style on the faces of the cube. Now, I'm not 100% sure how it's done, but I assume it's similar to the way that I do a pattern on the faces of my cube. The other thing is that the donut here is non-convex, and this takes a lot more maths. It's much more complicated to do. But we already knew this was an amazing demo. What else happened early on with regard to 3D rotation of objects? Well, I found this demo from 1996 called Virtuale Totalis Demo, and it's by someone called Pers, who won't try to pronounce his second name. I guess he's from somewhere in Scandinavia, and this is relatively early 3D rotation. So in a moment you'll see a 3D rotating cube with some kind of shading on the sides. It's done in a very different style than what I've done, and it looks like 40 by 25 text mode to me. But at least we found an example of an early demo that has 3D rotation. There isn't very much else in the demo along those lines. The next part is sort of pseudo 3D. It's actually just a repeating sequence of images that is supposed to look like you're going down a hallway in 3D, but this is not really what I would call true 3D. And the rest of the demo really isn't interesting for us today, so I'll stop it here. I thought I'd found a game which runs in CGA mode, which has some 3D objects in it. Very early DOS game called Alpha Waves, but this is what it looks like when I try to run it on either my XT or my 286. There is a video of it running in CGA on YouTube actually, so I'm a little bit surprised that I can't get it to run at all. Maybe there's just a corrupted version out there that I've got hold of. At any rate, I'm not sure that it was really 3D. It looked to me like the rotation was only in one direction and only over a small range. And I think this is just done with sprites, just in an animation. So we'll skip over that one and we'll move on to the games that our viewer found. The first game I'm looking at is LHX Attack Chopper, and in this particular game there are some sheds here near the runway. I'm just flying over those, and I think you can see that they're definitely 3D objects, and I guess there's about 3 frames a second. So this is still running on my 10 megahertz machine, so let's see when that one gets out of the way whether we get a higher frame rate. Not really. So there are some other options here, and I've currently got slow cockpit selected, and I've always turned the HUD off. So I think that this is basically the best that we're going to get out of this game. It's about 3 frames a second. If we actually quit this and end the mission, it'll show us the mission again without the cockpit, which will be a little bit faster. And you can see that, well, at least maybe 4 frames a second at the start there, before the sheds started to disappear out of range. So yeah, it looks like this is a 3D game. It's true 3D, not just pseudo 3D. And yeah, about 4 frames a second at 10 megahertz. The next game we're looking at is Abrams Battle Tank from 1989, and I apologise for the flicker. It's really just because the screen has a lot of white on it. But this is actually particularly impressive. If you look at this tank as it comes up here, you realise that it actually is a 3D object. Now, of course, this is an unplayable speed on this machine. It was designed for a much later machine, but you are getting about 1.5, maybe even 2 frames a second at some point. Okay, so it's not getting up around the 60 frames a second that we had, but look at the detail in this object. It's really quite impressive. So most of these games were of course made for VGA machines, and they're probably running on 386s or something like that, maybe just a 286, but at least they have a lot of detail here. I mean, there's a track, there are mountains, and the tanks themselves. So this is quite a good example of a 3D game running in CGA, and yeah, so I'm definitely going to pay this one. This is Stunts, and unfortunately the game itself doesn't run properly. If you try to start, it just doesn't get up enough speed to even get over the first jump, and then the track sort of disappears and so on. So I'm just running the demo here, and it really is like a slideshow. Basically, what I think is happening here is that it's trying to run the track at a certain speed, but because the frame rate is so low, you're just seeing flashes every now and again along the track. Nonetheless, you can see that it is rendering a whole bunch of 3D objects here, and I suspect the road itself, that they cheat with that a little. I'd be very, very surprised if there's any 3D in the road itself, but definitely all of the objects that you see are three-dimensional, and they're being rendered using the CPU. There's no math coprocessor in this machine. Now, bear in mind that this game came out in 1990, and by then the 486 was already out. So people were almost certainly running this on at least a 386, maybe a 486. And so that would explain why this is so slow. I mean, this machine is dozens of times slower than that. I was actually pretty surprised that this ran on CGA. It even runs on a monochrome monitor, which is pretty surprising. But that's basically a look at what you get for games in 1989, 1990 with 3D. It's still very, very low frame rates, but it's very hard to judge with a game because a game has so much else to take care of. For example, keyboard input, game dynamics, background scenery, and almost certainly everything here is being rendered to an off-screen buffer and then copied onto the screen, which virtually halves the frame rate before you even start. So I'm not too surprised at all that this game doesn't perform all that well. It is an impressive game, I have to say. There's an enormous number of tracks, and there's a lot of detail in this particular game. It's quite large, it's well over a megabyte, and there's really a lot of extras that they've packed in. You can even make your own tracks, I believe. So still an impressive game, just not meant to run on this machine. The last thing I want to show today is this demo by the Physical Crew, and this is the earliest demo I can find with 3D rotating polyhedra in it. So it's 1991, so very, very early. In fact, some of the members of this group apparently went on to form the group Triton, which is a very famous group that made a famous demo called Crystal Dream. And you can see here that we've got a rotating tetrahedron, which is much more comparable to what we were doing, and the frame rate here is very, very high. I have no idea what it would be, but it could easily be 30 or 60 frames a second. Now, of course, the difference here is this is VGA, as I'm sure you can tell from the colours. This is not CGA. And I'm not running this on my 8088 machine anymore. Unfortunately, it wouldn't run on there. It may just be an issue with the amount of memory in those machines, since the 286 and the 8088 don't have all that different an instruction set. But then again, they may actually be using it in some fancy way. But this machine at 12 megahertz, timings I've done say it's about 3 times faster than the 8088. So it's very hard to do a direct comparison, unfortunately. Nevertheless, I have to say that the speed they're getting here is absolutely phenomenal, even for a machine that's quite a bit faster. Now, of course, the VGA card also makes a difference. So you program this in a completely different way. It has bit planes instead of just bytes with bits packed into them for the pixels. And so I think that is making a difference as well, although it shouldn't be making a huge difference here. So this is a neat trick. I think what they're doing here is they're using the same 3D engine, but they're just using a 3D shape that just happens to be flat. It just has two sides to it. It's a really neat trick. I wish I'd thought of that one myself. And as they say, that's not all they've got. They do have something even better than that. And the next effect is really impressive to me. I'm really amazed by this running on a 286 at 12 megahertz. They actually have see-through sides. So this effect is called glance in the demo scene, and it's really a lot harder to do because you can see not just one side of each of the faces, but you can see the other side as well when it's on the back of the object, when you're looking through the object. So you're really doing roughly twice as much work as for the normal 3D rotation. So yeah, whatever they're doing here is really special. And the other thing that impresses me about this particular demo is the size of the objects. I think the resolution here is probably the same as what we're using, but the size is a little bit larger as well. So in every respect they're doing a really incredible job with this demo. So this is their final sort of geometric shape in the demo. It's again another lens. You can actually see through this one. And to finish it off, they have you know, a little starship shape that they rotate. That's all this demo does. It's just a 3D engine, and I guess we're looking at the early 3D engine of the Triton group in some sense. So really an amazing piece of demo scene history, if I've got my facts right there. And yeah, a really, really impressive demo. But that's all I have time for this week. Hopefully you enjoyed this. If you did, don't forget to like and subscribe. And we'll see you in a later video. Bye. There's a little addendum for people who made it this far. I decided to run the icosahedron demo on the 286 at 12 MHz. It still has the VGA card in it, it's just emulating CGA. But you can see that it spins around like crazy. In fact, it achieves 83 frames per second, which is nearly 3 times faster than what we had on the 10 MHz XT. Anyway, I just thought I'd show that. It doesn't look as good on here, of course it's not a CRT, but that's what the icosahedron looks like on the 286.